Everything we've talked about so far in our model of the universe was relying on the assumption that the universe is isotropic. It's the same everywhere. But that poses a problem, a really difficult problem that led to the theory of inflation, which is what we're going to talk about in the next few videos. Here's the problem. Let's say I look out in one direction, 13.8 billion light years away, and I see galaxies, stars, whatever, gas, microwave background, and let's say I look in the opposite direction, or any direction, to the same distance. So you've got two regions of space, 13.8 billion light years this way and 13.8 billion light years that way, and they both have the same density, they both have the same temperature, they both have the same everything that we can measure to incredible precision. Now, that's a bit weird. I mean, normally, if you see two things that are the same density and pressure and everything, it's because they've been in contact at some point. So let's say, for example, you have a bucket of hot water and cold water. If you mix them, they'll come into thermal equilibrium and they'll all be the same temperature, the same density, the same composition. So if we see things, distant edges of the universe, and they're the same, surely that indicates the two things were at some point mixed together.
Yeah, and so if you think about looking back, for example, to the cosmic microwave background, 13.8 billion years ago, you're going to look 13.8 billion years that direction, and then I'm going to look behind me 13.8 billion years the other direction, and you can ask, well, there's no way that part of the universe could have communicated with that part, because, you know, that's how long, you've literally used the entire age of the universe to go from that side of the universe just to us. And the other ones use the entire age of the universe to go from the other direction to us, which means they would need, you know, much, much longer to ever have a chance to talk to each other.
So these two regions are 27 or so billion light years apart, and the universe is not 27 billion years old. So how can they ever have communicated with each other?
Yeah, so that seems to be a missing ingredient, because when you follow the equations of the Friedman universe, that there is at no time those things will have ever been able to be in contact, even when the universe was really, really tiny, because when it was that small, it wasn't very old, and light still would not have had a chance to go from that side to that side. So we have a problem.
Yes, how do they know? I mean, it could just be that maybe God decided it was going to be like that. Let's make everything the same. Why not?
Yes, but I think here in science we want to try to come up for a reason. So we need to come up with a theory that naturally explains how it could have happened. And that's one of the problems, but it's not the only problem. We actually have two other problems. One of the other problems we have is if we go through and we look at the universe, we see that it's very close to having that magical value of density, which is where it's flat, where k equals 0. And you wouldn't expect that, because if the universe is a little more dense than that, or a little less than dense than that, it wants to sort of run away from that magical value.
Yes, so let's say when the universe was a nanosecond old or something, it was a little bit more than the critical density. The critical density then would have been much more than it is now. But let's say it was 10% more than that. That means the universe would recollapse, get smaller and smaller, which means the density will get higher and higher, which means it'll be even further off the critical density, which means it'll contract even faster. So as if the universe was a little bit lower than this density, then it'll expand faster, the density will drop even more so. So you'd expect if the universe is anything other than critical density, it would run away one side or the other. If it was even 1 part in a million off just after the Big Bang, it would now be hundreds of orders of magnitude off one way or the other, vastly more dense or vastly less dense. We don't know the universe is exactly if this k equals 0, but we know it's pretty close, within a factor of 10 or so. If it's within a factor of 10 now, it must have been within a factor of millions of decimal places just after the Big Bang. Once again, why?
So we'd like a theory to fix that. And then there's the other problem, is that we're here at all. And we're here because gravity was able to take a part of the universe that was a little denser right after the Big Bang and collapse it down. And indeed, there's a pattern of density fluctuations, or lumps and bumps, that the universe was born in that doesn't really, kind of defies explanation. It's almost like the universe was born with white noise. So that static we hear on radio, there's a certain amounts of bumps and lumps that are equal across all scales, and we need to understand why that happened.
Yes, we've been assuming the universe is uniform, but of course if it was totally uniform, it would stay uniform. Nothing would ever form. It would just be steadily colder gas and radiation as the universe got bigger and bigger. We need there to be lumps to turn into stars and galaxies and clusters of galaxies and superclusters. And the interesting thing, as you've said, is that it turns out there's structure on all scales pretty much. There is small lumps that turn into small things like galaxies and big lumps that turn into big things like superclusters of galaxies. And as far as we can tell, the amount of lumpiness on all these different scales is about the same.
Yep.
And where did these lumps come from? If they weren't there, we wouldn't exist. So we're very glad they're here. But where do they come from?
So inflation as a theory was dreamed up in the early 1980s by Alan Guth and a number of other people. Seems to sort of be the panacea to all these problems. It can explain these three fundamental questions we have about essentially the initial conditions of the universe.
So let's talk you through this theory of inflation now.